Alright, welcome to a new set of slides. This one is on functions and relations. Functions in the mathematical sense, not quite the programming sense, but it will seem very similar, because that's of course what programming functions are based off of, mathematical functions. So a lot of this you've probably already seen from math. Here's a funny meme about it. And yeah, let's get right into it. Let's talk about the functions that you know and love from like a math class. So let's define everything. Start from first principles as usual. So a function, you can give it a name, function f. What it does is, well, let's say that we have a function that takes elements of some input type, some type x, and it spits out elements of some output type called y. So it's just taking elements of some set to elements of another set. What is that but a subset of x cross y? It's just a bunch of pairs, like for this x input, I give you this y output. That's all. So that's the first bit of a function, and it's a special kind of subset of x cross y. For every x on the left side of the first piece of the pair, there is only one y. There's only one corresponding output for that function. All right, so let me try and have that make a little bit of sense. So like here is x, here is y, they are sets, and essentially in function land, it's saying, all right, here are the three elements of the set x. Let's pretend there's only three elements, x1, x2, and x3. And let's pretend that we have a function f on x as inputs, and then it's outputting values in the set y here. So here's all the elements of y. Let's say that there's only finitely many. y3, y4, and what a function does, a function f does, is it takes every input and it spits out some output. So like maybe x1 maps to y2 and x2 maps to y1. And x3, like it gets a choice. I mean, it can go to any of them, but let's say that it goes to y4, and so we're skipping out on y3. This is the function f. F is that green thing. It's just telling you what's going on, okay? So normally we think of functions like this. It takes inputs and that's its one output, exactly one thing, but you can also think of it as a subset of a Cartesian product of x cross y. So f, in math, here's how we can define f. This is exactly what f is. It's saying it takes x1 to y2, it takes x2 to y1, and it takes x3 to y4. That's how you can define a function. All it is, it's just which pieces, which inputs map to which outputs. Okay? And the exactly run rule is very important. Like x1 can't map to both y1 and y3 at the same time. That's no longer a function, right? So that's important. And yeah, for every input, there's exactly one output. And other names for those things, I think you've heard of them, like x, it's the input, it's called the domain. That's the fancy mathematical name. X is the domain of the function f. And then we call y either the target or the codomain. We say target or codomain, either one works. That's just the set that you're spitting out when the function gets called. And it doesn't have to cover all of y, like you're kind of forced to. If x only has three elements, you can't cover all four elements of y. You gotta like leave somebody out, or potentially leave three people out if they all map to the same value. So yeah, at the end of the day, a function is just a bunch of pairs. It's just a bunch of pairs of inputs and outputs. That's how you can define one in math. So yeah, let's talk about some more terms before we move on. So if f takes an element of the domain to 0 elements or more than one element of the target, then f is not really a function. It's not called well-defined at that point. So for example, if I forgot about x3 and x3 doesn't map to anything, it's not a well-defined function. And if x3 maps to multiple values, like call f on x3, like maybe the answer is y3, maybe the answer is y4, sometimes, that's no longer a function as well. It should only take an input to a single output. Okay, so that's what it means to be well-defined. You're not doing anything silly like that. And then finally, the word range is probably what you thought that y was, but range is very, very special. Range is not the same as the target or the codomain. The range of a function is all the values that are being hit in the codomain. So it's the set of all the y's such that x comma y is in f, so it's being mapped to by some x. Okay? So for example, in this example function, this one right here, using the arrows, let me make it a well-defined function again. The range of f is all the y's that are being hit. So y1 is being hit, y2 is being hit, y4 is being hit. And so that would be the range. y1, y2, y4. And notice that's not the same as the codomain, which is all of y. Okay, so that's the main difference. The range is the values of the set that are actually being hit. That is the key difference that maybe, I don't think I was really told very much about that in my other math classes, so that's a new thing to remember and hold on to, I guess. All right, even more terms, of course, because this is a new set of slides. Let's say this. So let's pretend we have a function. This colon symbol is saying what the domain is and what the target is, or what the codomain is. So f is a function that takes integers to integers. That's how you read it. And then here's its definition. F of some x outputs the absolute value of the input. All right. So for example, f on negative 42 takes the absolute value and spits out positive 42. F of 3 keeps it as 3 because the absolute value of 3 is 3. F of 0 is 0. It's that function. All right. So what's the domain? What's the target? What's the range is the main question here. Well, the domain is all of the integers. You can only give f an integer. That you can read off very easily. And the target's right there too. It's all the integers. And that's not the same as the range, is it? Because the range is all the values being hit as the endpoint, as the resulting value of some input. And if you think about this long enough, like here's the number 0, the absolute value function, it takes all these values, like here's 1, 2, 3. It takes them all to themselves, right? All positive values are taken to themselves. 0 is taken to itself. But like the negative values, like if this were negative 1, here's positive 1. Negative 1, the absolute value is taking that to positive 1. You see that? So all the values being hit are on the right side of the number line. Here's the range. The range starts at 0 and it goes that way. You see that? That's the range of this function. It is only the positive, the non-negative numbers, because 0 is included. 0, 1, 2, all the way on to infinity. It's the integers only, though. Integers starting at 0. So we have a name for that. That's called the natural numbers. The range is the natural numbers. It's not the same as the target. Okay. So I guess the target could have been a bit more precise if we wanted to make it more precise. And notice that f is defined only as being able to take integers. It can only take negative 42, 3, 0, all those numbers like that, whole numbers. You can't give f like pi or something. That would require a function that has a different range, a different domain. So the alternative would be make a function g that's defined taking reals to reals. That would be a different function, not the same as x, or as f, right? G of x, again, returns the absolute value. That one would actually work on decimal values, 3.1, negative 3.14, I guess. G of negative 3.14 would be sent to positive 3.14. And that's allowed because now that's an element of my domain. But pi is not in z, therefore we cannot call f on it. Okay, hopefully that makes enough sense. And functions can be equal. Maybe they get their answer in a slightly different way, but as long as they have the same domain as and target, and their values agree, like if you call f of x, that's the same as g of x for every possible x in the domain, that's called functional equality. Those two functions are equal to each other if they have the same domain and target, and their values are equal. So even though g and f are defined with the same code, they are not equal functions because their domain and targets are different. One works on reals, the other works on integers. Okay, I hope that makes a little bit of sense. It's very technical, but we need to go there because that's what you have to learn. That's what you're required to learn in this class. All right. So here is a question for us to try and get all this straight in our minds. So here's a diagram, took it from the book, and so here's the function f, it's all the red arrows, and here's the function g, it's all of the green arrows. And I'd like you to tell me what are the domain and range of f and g, And also, are they well-defined functions? So maybe you want to, I'll go back to this slide so you can remember what the definition of well-defined is, and then, yeah, give this a try, and then we'll talk about it. So f and g, what's going on? So f, I need to talk about their domains, I need to talk about their range, and then we need to talk about well-definedness, but I guess I need both of these, so let me save myself some drawing. There we go. So what's the domain of f? It is all the values being sent somewhere. So it looks like A, B, C, and D are all the left side of some arrow. Therefore, the domain of f is A, B, C, D. It's that set. I hope you got that. And then the range of f is all of the values being hit. It's all the endpoints of some arrow. So it's W, X, Y, and Z. W, X, Y, and Z. And to be well defined, we have to make sure that we're not like forgetting about an element of our domain, and we're not mapping a single element of our domain to more than one element of our target. So let's make sure that's not happening. It looks like A, B, C, and D, they all have an arrow coming out of them. So that part's good. But look at B. What is f of b? Well, it's w and y at the same time. That makes no sense. So that's not a well-defined function. Okay? So f is not well-defined. Because of that, it can't take a single value to multiple places. Functions don't do that. It's not a well-defined function. All right? Yeah, let's talk about g now. So the domain of g is all of the elements that are the source, the left of an arrow. So it looks like A, B, C, and D again are the domains. A, B, C, and D are the elements of the domain, and the range is all the people being hit. So it's all the things on the target of some arrow. So it looks like it's W, X, and Z. W, X, and Z are elements of the range. And are all the values of the domain being taken somewhere? Yes. Are any values of the domain going to multiple places? No. So this is a well-defined function. Is well-defined. And that's nice. And notice that it's okay to have multiple inputs going to the same output. Like that's like the absolute value function does that, right? 42 is equal to the absolute value of negative 42. Those are both going to the same place. It's okay to hit the same thing twice, but you can't go multiple places from the starting place, from a starting point. That is the trade-off. All right. I hope that makes enough sense. Please yell at me if it does not, but hopefully that's getting us some practice with those definitions. All right, here are some more. So here are two functions, f and g. Let us define them this way. They take a pair. F takes a pair, an element of z cross z, so a pair of two integers, and it takes it to a single integer. You see that? So it's taking two things. It's a function of multiple inputs, takes two integers and sends them to a positive, looks like non-negative integer. That's the absolute value of x plus y. And then here is g, takes again a pair of integers to a single integer, and it performs this. Absolute value of x plus absolute value of y, and looks like I added an extra space for no reason. So does f equal g? So let me scroll back to the functional equality definition, stare at that for a second, and then you try this. Tell me if f is equal to g. All right? So, what are the two requirements? You need the same domain and codomain for each function. And then you need the functions to agree on every input. If both of those are true, then the functions are equal. So do these have the same domain and codomain? Yeah, they're both taking a pair of integers to a single integer, so that's cool. But do the functions agree? And I don't think it should take you that long to find a counterexample, but if you call f on 2 and negative 2, and you call g on 2 and negative 2, the fact that this is all done, like the plus is done before the absolute value, and the absolute value is done before the plus in g, that difference is going to affect the outputs. So f of 2 and negative 2 is going to compute 2 plus negative 2, and then take the absolute value, which is going to be 0. And then this one is going to do the absolute value of both, and then sum them, so that's 4. You see how those are not equal? So the functions don't agree on this particular pair of numbers and infinitely many others. So therefore, the whole thing, they're not equal functions, right? They have at least one element where they don't agree. All right, so that is kind of the proof. It's a counterexample. It shows that the functions are not equal. Okay, I hope you got that. So let's see here. Moving right on, let's talk about the floor and the ceiling. They're special functions. This is useful when we're rounding. When we're doing integer division, essentially a floor is being taken in C++. So it's good to understand the mathematical terms. So the floor function, what it does is it takes a real number and it spits you out an integer. It's the nearest integer in the downward direction. All right. So the floor of x is the largest integer y such that y is less than or equal to x. And it's a bit weird. The notation looks like here's the ground. It's drawing some brackets that only have the bottom half. It's the floor of x. All right, that's how you write it in math. But essentially, like this is the floor of x. Like the floor is on the ground. It's shoving x down to the closest whole number that's smaller. And the floor function is your cast double to an integer, if you remember that. Static cast into an int of some double, like 42.5. That's going to send it to 42. It's going to chop off the decimal places because that's the nearest whole number that's smaller. See that? So that is, that's what the floor means. It's just go to the nearest whole number that's smaller. So 3.14, it's going to 3. It's sending a real number to an integer. 42.5, going to 42, chopping off the decimal places. The floor of 394, it's the closest whole number that's less than or equal to my current number, and this one's already a whole number, so it gets to stay 394. I hope that makes sense. All right, so that's the floor function. The ceiling function is the opposite. The metaphor is you're in a room, I guess, and you're shoving something down in the ground or throwing it up into the ceiling. So the ceiling function rounds a real number to the nearest integer in the upward direction, so it's the nearest number that's bigger. So ceiling of x is the smallest integer, y, such that y is greater than or equal to the input x. And the notation is exactly what you would expect. It is this end of the brackets, and so it's rounding up. All right, so 3.14, the ceiling of that, it's the next bigger whole number. So it's not the normal rounding rules, it's 4. Okay, 42.5, the ceiling of that is 43. And then ceiling of 394, it's the nearest whole number that's bigger, well, or equal to it. And this one's already a whole number, so it's 394 again. All right, so those are some functions that technically you've already been using in C++. This idea of integer division involves the floor function. And now you know. Now you have the mathematical words to describe it. All right. So with that in mind, using this floor function or this ceiling function, I have a question for you to try. So here is a fun example that involves real life and the floor and ceiling function. So let's pretend this. We have a baker, and the baker is packaging cookies for sale. He's made a bunch of cookies, and the cookies come in boxes of 8 cookies in a box. And he has y cookies total to put into boxes. And the question is, how many full boxes can he sell, right? Because it's got to be at least, it's got to be exactly 8 cookies in a box. And he has y cookies total. So please use either floor or ceiling to describe how many cookie boxes this baker can sell. All right? So think about that for a second. Try some examples, I think, would be very helpful here. So, here we go. If y is equal to 24, like he has exactly a multiple of 8 cookies, he can make 3 boxes, right? That's pretty easy to see. What if he has 25 cookies? Like he made a multiple of 5 cookies. Like he has 25 cookies total, but he needs to put them into boxes. How many boxes can he make? Again, right? He can't make a fraction of a box. He can only make 3 again. You see that? And he's going to have 1 left over. So that should scream, there's a division going on, right? It's like y over 8, essentially. And it's, if you do 25 over 8, that's 3 point something, something, something. But we want the 3, and it's going to be the floor operation. It's, all right, however many whole multiples of 8 you have, that's as many boxes as you can make. And so, like, if you divide by 8 and you get, like, I don't know, you made a bunch of cookies, and you only get, like, 1,000.99999. Again, it's the floor. The baker can only make 1,000 boxes of cookies. He does not have enough to make an 1,001th box, okay? That's the idea. He does not have enough still. So it's always a rounding down process. It's the floor function. Did you get that? I hope that's starting to make a little bit of sense. So yeah, just something that you understand, just new notation, I guess, I would say. So yeah, let's keep on going then. So let's talk about some properties that functions can have. These, I think, you should have seen before in a math class, most likely. So just some review, I think. So a function is called one-to-one, or also injective. That's the fancy Latin root way of saying that it's one-to-one. A function is one-to-one or injective if elements that are non-equal map to non-equal outputs. That's the definition. That's how you define it. So the way that you might say that in English is like f maps different elements in x to different elements in y. And so that means it's never going to hit the same place twice. Every one gets another one. One-to-one. Okay? So here is an example of a function that is one-to-one. It never hits the same place twice. So like, I don't know. Let's say that the domain is 3 elements and the codomain is 4 potential elements to hit. So a function that is one-to-one always takes input values to different output values. Like that one's going here, so this one can't go here now. It's got to go somewhere else. So let's make it go here maybe. I don't know. And then this one can go somewhere else as well. So that's a one-to-one function. And a function that's not one-to-one looks like this. So an easy way to make a function that's not one-to-one is to have a smaller codomain than your domain. So here's like x, y, and z, I don't know, a and b. And so let's see here. Let's send. You're kind of forced, right? You're forced to like send multiple values to the same place because you have 3 inputs and 2 outputs. So you're forced to make z go to somewhere that's already been seen. And the reason this is not one-to-one is because like this implies this. Well, we have that y is not equal to z, but this is false. So it's not a correct implication anymore, right? It's a false thing. But f of y is equal to f of z, and that was not allowed. So sad face, that is going to give us a non-one-to-one function. All right? Hopefully that is coming back to us. It's just f never hits the same place twice, but this is the mathematical definition of that. x1 not equal to x2 implies f of x1 not equal to f of x2. All right? A function is called onto or surjective. Again, that's the Latin root cool way of saying it, I guess. A function is onto or surjective if the range of f is equal to the target y. So if the entire thing, like every element of the target is being hit, it is the range. Okay? So for every y and y, there is an x such that f of x is equal to y. That's how you can write it in math. And then informally in English, you could say that f hits every element of the target / codomain. So that was the most precise way of talking about what's being hit. So here's a function that's onto. All of its elements are being hit. I don't know, doesn't really matter. As long as the domain is at least as big as the target, you can make at least one function that works. So I don't know. Maybe that one hits there, but this one can hit here. So all the elements of the range are being hit by some input, and so that's an onto function, if assuming these 3 elements were the entirety of the range, or the target. So that is a function that is onto. Here's a function that's not onto. Let's pretend that all these things on the right, this is the entire target. So if the domain is smaller, you're kind of forced to have a function that cannot be onto. So you're always going to have somebody left out. Or if you have multiple input values mapped to the same place, that's another way to make a non-onto function. So again, there's an element of the target that is not being hit. Like the range is just these first 3 elements. It's not this last one. Okay? So that's a function that's not onto. So one-to-one or injective and onto or surjective. Okay? Let's talk about more Latin roots. So a function that is both one-to-one and onto, like bi, right? Two-ejective. It's both ways. So a function that is both one-to-one and onto is called bijective, and a bijective function is called a bijection. Makes enough sense. Or a one-to-one correspondence. And so that is a cool idea. It's a very powerful thing to have a bijective function that is both one-to one-on-one, and one-to-one, and onto. I can't keep those words straight in my mind apparently. So yeah, let me show you a function that is bijective. It is this one. Here are my two inputs and outputs. So here's the domain, here's the target. So what does it mean for a function to be both one-on-one, one-to-one, and onto? So to be one-to-one, every input goes to a different output, and to be onto, every element of the target is hit. The target is the range. So this is a function that is bijective. Okay, hope that makes sense. And when you have a bijective function, hopefully the diagram is kind of making it obvious. When you have a bijective function, you can always go backwards. You can always figure out, like, for this value, what was the one element of the domain that got me to here? There is an inverse. You can always invert your function. When you have a bijection, an inverse always exists, and it's called f. That's how you write it, f inverse, f to the negative 1. And it goes backwards. It takes your y to the x that took you there. All right? Let's just go backwards. For each xy pair, go in the opposite order. So it's like, here is the inverse. Inverse of f. Go backwards. Go backwards. Because you can always go backwards. It's always well-defined to do that. All right? So yeah, the inverse of f, therefore, would be, if you just wanted to write it out separately, here's xy again. X and y, the inverse of f goes in the opposite direction. It's going to be like this. Boop. Boop. And then boop. Okay, so yeah, formally, mathematically, the inverse of a function f is all the yx pairs where there was an xy pair in f. So let's just take this input-output mapping and flip it around. Now the output maps to the input. That's what it means to be an inverse. Okay, just swap those things, and I'd like you to think about this on your own. It would help you understand, like, why the inverse is always well defined. What breaks down, like, when a function isn't one-to-one? How does that affect the fact that there can't be an inverse anymore? If it isn't onto, how does that affect the fact that you can't have an inverse from y to x anymore? All right. So I'd like you to think about that. That would very much help you with these terms and these ideas, I think. So with that in mind, let me give you another question to try. So I'd like you to find the inverse of the following functions if it exists, if the inverse is actually well defined. Okay? It may not be. So some functions don't have an inverse, and I want you to figure out if one of these does or does not. Okay? So if it exists, find it. Otherwise, tell me that it does not exist. So here are two functions. F goes from integers to integers, and f of x is equal to x plus 3. And then here is g. Do it for both. G again takes integers to integers, and g of x takes any x to 2 times x plus 34. All right, so see if you can find an inverse of either of those. Maybe both. All right, so let's see here. So for the first one, for f, let's see if we can find an inverse of f. If it's not clear that it does or does not exist, maybe you can draw some inputs. So here are some potential values of z. Here are some other potential values of z. If you think about it, like, what is f doing to integers? So like, it's taking -3 and it's adding 3 to it. So it's sending -3 to 0, sending -2 to 1, it's sending -1 to 2. Do you see how, like, it's kind of just shifting the integers around a little bit? And so you can always go back to where you came from. Like 0 is always going back to -3, 1 is always going back to -2, and you always have some value that you can go back to, like up here, up here. You can offset it as much as you need to. So every element of the domain is being hit, every element of z is being hit by this function. It's just being offset a little bit. So that means the inverse exists. And so what in the world is the inverse? It's just, well, you kind of just swap the x's and y's. You remember doing that? Like, this is y, this is x. You just solve for, like, you replace x and y, swap them, and then solve for x now. Something like that. That's how you did it in math class. So, yeah. This is, let's swap x and its inverse. So here's how you solve for the inverse. X is equal to, because you swap it, like, what is the inverse of f of x? It's just the x. What's the inverse of x? It's, you call the inverse on it. Ooh, my computer was did a little weird thing there. Hopefully it's still recording all right. So f inverse of x plus 3. So you turn f of x into just x, and then you turn x into its inverse, and then you just solve for the inverse function. So the inverse of x, just write it like this, right? F inverse of x is equal to, well, you just bring the 3 over there. So it's equal to x minus 3. And so that's the inverse of the first function. It exists. It's cool. For the second function, does that one have an inverse? So if you think about it enough, let's see here. You can kind of do that same process. You just solve for the inverse. You kind of like flip these two. Every time you say g of x, replace that with x. Every time you say x, replace it with g inverse of x. So you can do that same pattern. 2 times g inverse of x plus 34. And assuming this all works out, like what is the inverse? This is like x minus 34 is equal to 2 times g inverse of x. Solving for g inverse of x. G inverse of x is equal to x minus 34 over 2. Okay, interesting. And remember, the inverse must take the target to the domain. It must go backwards. So z to z again, just in the opposite direction. So this would be the inverse, but does it exist? If you think about this long enough, what's g of 0? It is 34. What's g of 1? It's 2 plus 34, so it's 36. Where is 35? We have to be able to go backwards from every element. What would be g inverse of 35? If you solve this, it's x minus 34 over 2, so it's like 35 minus 34 over 2. That's 1/2. That's not an element of z. You see that? You cannot start from 35 and get to some input element that took you there, because it's not an integer. That would have to be a rational number, at least. Do you see that? So that's unfortunate, and that's telling us that we have a value of the target that's not being hit. The target is not the range, and so g is not an onto function. You see that? It's not an onto function. Therefore, we cannot invert it, because there's no way to come from 35 back to some starting point that doesn't exist. So g is not invertible, we say. And I hope that makes enough sense. That's kind of how I want you to think about it. Is it 1-to-1? Is it onto? This one was 1-to-1, but it's not onto. So you can't invert it. Okay? Okay. So yeah, with that in mind, I think, I just have one last concept before we head out for the day. Let's talk about function composition. Again, something you should have seen before in a math class, but let's talk about it in more detail. So function composition looks like this. You say g, then you put this little circle, then you say f, and it's you read it as like g after f, or g composed with f, because you kind of do f first, right? It's f, then g, so g is done after you do f. It's a way of combining functions to make a brand new function. It's a bigger function that does both, kind of, right? G composed with f means to apply g after you apply f. So here's an example. F takes an integer to a natural number, and so it takes an input to its absolute value, and then g takes a natural number. Notice how these kind of have to align here, like these better agree if you want to compose them. It takes a natural number to a Boolean value, true and false, and so g of x is asking the question, is x greater than 2? And so if you apply their composition, g composed with f to the value -5, what happens? It's apply g after f. So take f, apply that to -5, and then apply g right after it. Okay, you see how that's working? So you apply this one value to the whole composition, which is the same as give the first function, the one on the right, that first value, get its answer, and then shove that into g. Okay, so f of -5 is equal to +5 because it's the absolute value function, and then g of 5 because 5 is greater than 2 is going to give back true. And so that's the final answer. Does that make sense? That is how that works. Okay? And so yeah, every time you see this, g composed with f, applied to some value, this is one bigger function. That's their combined version of applying g after f on x. Okay? So that's how that works. And again, when this happens, when you have functions, you can only compose them if the range of the one on the right, or sorry, the codomain of the one on the right is equal to the domain of the one on the left. So here is this. These better correspond. And to true and false. So we needed this, right? We needed these to align, otherwise we couldn't give this one's result to this one as an input. You see that? That's important. So those better match, and then their composition is now then going to take the first one's input to the final output. Like it's a way of going straight from z to true and false. That's what the composition of these two functions do. Okay, so that's that. Let's see here. We can do these first two examples then. Let f be from a to b and g be from b to c. So what is the type? Like what is the input and output? What's the domain and target of g after f? G composed with f. So g takes a b, gives you a c, or sorry, you start with f first. F takes an a, gives you a b, and g will be able to take that b and give you back a c. So their composition takes the first value, takes the a, and goes all the way to c. So you see how they align? It's like these ones are equal, and then it's taking a all the way to c. A to c. What about f composed with g? It would take, right? It would do g first, so it's taking a b. So b would be forced to be the domain, and then it gives you a c. Then you need to somehow plug in a c as the input to f. But f takes an a. So this doesn't work, right? That's not possible. It's not defined. You cannot compose in that direction. I hope you see that. All right. Next, we have the identity function, which is a very standard function to want to use. The identity function on a set A, you call that I of A, and it maps every element to itself. So the identity function on the set A takes an A, gives you back an A. It gives you back the exact same input. So I of A on some value gives you back that same value. I of A on A gives you A for every A and A. So that's a lot of A's. Hopefully that makes enough sense. If you think about it long enough, like here is the identity function on numbers. If you give it a 5, it's going to spit back out the 5, right? Or any other number. The identity function on integers, if you give that 42, it will give you back 42. It just gives you what you gave it. So it's this function. It's like take every input to the same value. Straight lines. Okay? So it's usually always possible to compose with some identity function as long as the types match up. So let's see here. Let's try this one. Can you compose f with identity on a? So identity on a takes an a, gives you back an a, and then f takes an a and gives you back a b. And so those actually correspond. That's going to work out just fine. And so this would give you take an input value, give you back an input value, give you back the same value, and then call f on it to give you back a b. And so the types match up. It's a well-defined function. What is it equal to, though? If you think about this long enough, composing on the right with the identity doesn't really do anything. It does the same as f total, right? Because look at this. F composed with the identity on A is applied to some element of that set A. That's equal to, first do the identity on A function, call it on A, and then apply whatever that gives you back to f. Apply f on that. What is I of A going to give you back? It's always going to give you back A, so that's equal to f of A. So the composition is just equal to calling f. So that's equal to that. And so that's essentially multiplying by 1 in function land. All right, what about this one? F compose on the right with identity. So identity of A after doing f. What about these? So again, f is a to b. And then the identity on A would be from A to A, of course. So this would take an A, give you back a B, and then try to apply the identity on that B, but now it's the wrong type. It's the wrong set value. So this one's not defined. I hope you see that. They don't match up. All right? It's just like this problem all over again. What about this one? Identity on B first, then F second, right? Because it's always the thing on the right happening first. So this is taking B's to B's, and this is going from A to B. And if you compose them, it's going to call the identity first on some B value. So B is the domain of the composition. Gives you back a B, and then you try to use F on that B, but F takes an A. So again, it's not defined. And then finally, this one's going to work. That's the opposite. You kind of had to switch the types around when you moved the identity to the other side. So this one, f again, takes an a, gives you back a b, and so the input's an a, spits out a b, and then you give that to the identity on b's, which takes that b, and now they do match, and gives you back another b. So that's perfect. So it takes that b from f's result, and plugs it into the identity on b. And for the same reason as this one, that's again going to be equal to just calling f. All right? There is no need to compose with the identity. It would have done the same thing. Okay? Please yell at me if any of that doesn't make sense, but we're just using this concept from a math class in a bit more detail now. All right. So with all that taken together, let's see if I can get you to try this one. Here are two functions, f of x and h of x. They both take z's to z's. It takes integers to integers, the same domain and target. So they're going to compose just fine. And here they are. F of x equals 2x plus 3, and h of x equals x squared plus 1. Give a formula for f composed with h. F done after h. Can you do that? An explicit formula where you're not just saying f call h, then call f. Can you combine these into one bigger function? Like, what is this explicit formula? Like, their composition is equal to some weird expression involving just x, not just calling the functions anymore. All right, so try that. See if you can find the mathematical expression that is equal to their composition. And assuming you tried that, here's how I like to think about it. So what's f after h on x? What's the composition? Well, that's the same as calling f on h of x's result, which is the same as calling f on whatever h of x gives back, and that gives back x squared plus 1, right? So it's calling f on x squared plus 1, and that's the input. You see that? And so now you get to treat x squared plus 1 as the x in the definition of x, f of x. You see that? That's how that works. And so every time you see x in the body of f, replace that with its input, because that's my input to f right now. It's a big expression. So if you think about that long enough, it's equal to 2 times its input, right? F of x is equal to f of its input is equal to 2 times its input plus 3. Its input is now x squared plus 1, so it's 2 times that plus 3. So that's equal to 2x squared plus 2 plus 3 is 5. So that is the composition. That's the explicit formula for it. So f after h called on x is equal to 2x squared plus 5. That's its explicit formula to compute the answer once and for all, not having to individually call f or h anymore. We kind of simplified the answer. All right? That's the idea there. So that's where I would like to stop today. I think that's a good stopping point. We'll come back, and functions were first. I promised another thing called relations, those you have not seen before. That's where we will go in the next lecture. So I will see you there.